Hey guys, welcome back. Day 39. We're doing thermodynamics, heat transfer. All right, so this is kind of exciting. And thermodynamics was developed to investigate how we can make heat into work. Heat into work. All right, we're going to define everything. And so we're going to look at this through, obviously, chemical reactions, right? And we have reactants react, and products are produced. All right. So, what's going on here? Reactants, bonds are broken, and products, new bonds are formed. All right. And so, this chemical reaction is a rearrangement of atoms and a redistribution of electrons. So we're moving atoms and electrons around, all right? And there's energy involved, okay? What is energy? That's a great question, right? Energy, this energy, right? So if we look, what is a joule, right? Energy is measured in joules. And joules are, of course, if we break it down, Newton meter. All right. And so a joule is a Newton is mass times acceleration. Mass times acceleration, so kilogram meter squared per second squared. So energy is what's required to take a kilogram of water and move it a meter. Right? That's kind of like what we measure energy in, right? And it comes in different forms. Right? We have light, photochemistry. E equals H nu, right? We already talked about that previously, right? So you go outside and, the sun's energy gives us, this planet, warmth and all sorts of things. Electrical energy, you're probably using electrical energy right now. We got electrochemistry. Right? And volts is joules per coulomb. We talk about that exclusively or extensively in Chem 2. Right? And another one is, there's also nuclear, which is not really chemistry, where you got E equals mc squared, right? So you have mass going into energy. Right? But we're going to talk about heat, which is thermochemistry. Right? And we use these terms, energy and heat and whatnot. And so we're going to dive into more what these things mean. So now in thermochemistry, if heat is released in a process, it is what we're going to call exothermic. So it means like exoskeleton, right? Outside. Heat's released. Heat absorbed is endothermic. So inside. All right. So quick example. If you have a grill, whether you are a propane grill, gas grill, you have a pellet grill, charcoal, you just use wood, right? Whatever you use for your grill, the burning of whatever fuel you're using, that is an exothermic process. Whatever you're cooking on your grill, that food going into what you start with to what you want to eat, that's an endothermic process. So the grill's exothermic, the food's endothermic. All right. So we talk about energy here. There's two basic forms that we talk about: kinetic and potential. All right? Kinetic and potential. And so kinetic, you think motion. Right? Basic physics, 1/2 mv squared. Right? Motion. So moving particles, moving objects. Potential is position. Some people call it stored, right? Now, PE equals mass, acceleration, usually due to gravity and how high you are, right? So if you're on the first story to jump out the window, okay, not a big deal usually. On the second story to jump out the window, I don't know. Probably not going to happen. Now, if that's the only way out, you need to go. But we don't really want to jump out of high windows. It doesn't work well for us. All right? Now, chemical potential energy, because we're talking about chemistry instead of how high something is, right? Chemical potential energy is energy, basically how the atom's made, right? Okay, it's stored within the structure of the molecule or compound, right? It's stored within the molecule. Let's write that down. All right, it's a lot of it's due to the electrons and how they're configured to nuclei in the whole, right? But it's stored. It's energy stored within the compound. All right, the compound. Let's call it the compound's structure. All right, so because of the atoms are the atoms, but how they're put together and how they're arranged, there could be energy in there, right? And we like to take that energy and do work with it, right? And we'll define all that. So the first thing we have to define is the system, right? And the system is what we're looking at, okay? Now, the system can be anything, right? It's a part of the universe under an examination. So for us, chemical reactions or this chemical compound, this substance, right? But I mean, a system could be you're looking at a car's fuel system. You're looking at the car's aerodynamic system. You're looking at a system of networking, right? Like there's all sorts of different systems you can talk about. But for us, we're going to talk about chemicals, all right? And so when we talk about the system is, I'm just going to draw a circle, is the part of the universe we're looking at, all right? Then outside of the system is the surroundings. Right? And so all together, the whole thing is universe. Right? So in the whole universe, we look at one thing, and then everything else in the universe is the surroundings. So if I have a 5-gallon bucket of gasoline, and that's my system, right? Then everything else in the universe is the surroundings. It seems kind of overkill, but that's how it's defined. Now the system has something called U. And U is the internal energy of the system, right? So that's weird. All right. Okay. But that's what it is. And so what we can do is we can put energy into the system, or you can take energy out, right? So we can put energy into a system and we can take energy out. How can we do that? What do you think we can do? Well, the first one makes sense is we could heat it, right? You can heat the system. The second one's not so obvious, maybe. Maybe it is for you, science people, okay? But you can do work on it. Okay? All right? So now delta U is the change in internal energy. So what is delta U? Delta U, right, is going to be equal to the heat plus the work. The heat is Q, and the work is W. Heat and work. All right. Now, we're going to look at this through the lens of the system. All right. Just like money, $20 is $20. It might not be worth the same as it was 5 years ago, 10 years ago, 20 years ago, but it's still $20. Okay. It has a value of 20 American dollars. If we think about this, $20 is always positive. Right? We're always positive with $20. And so if I give you $20, that would be a positive $20 to you. If you gave me $20, it would be a negative $20 to you, right? That's because we look at it through our own eyes. That's how we look. Well, energy is the same way. Energy can't be negative, just like money can't be negative. You can owe somebody money, but you don't have a negative $20 bill. That would be weird. Oh, happy birthday, here's negative $20. That doesn't work. All right? Okay, so it's all energy is positive too, and we always look at it through the system's lens, right? And so either the system's gaining energy and the energy is positive, or the system's losing energy and the energy is negative. Hopefully that kind of makes sense. All right? And so it's always positive if the system's gaining energy. Right? In some systems we want to use that lose energy, like your gasoline in your car, your whatever you use for your grill, right? We're using those chemicals and we're losing heat from the system, and that's what we want, all right? Okay. And so now your book tells you a couple different things, right? Open systems can exchange mass and energy, right? Like humans, we're very open systems. Closed systems can only transfer energy. And isolated systems has no mass or energy change. All right. Now, the system has a state. Okay. Now, this is not necessarily the same as a state of matter, but it has a state. All right. Composition, energy, temperature, pressure, volume. These are how it works. All right. These are the conditions, the states of how it works. All right. And those are important to how things operate because, as you know, I live in eastern North Carolina, and half the time if you leave your phone out in the sun, right, most of the year, it tells you, your phone will tell you it's too hot to operate after a few minutes, right? It'll give you whatever that symbol is, and it doesn't work, right? Because your phone has an operating range. Your cars have operating ranges. Your TVs have operating ranges. Everything we have has operating ranges. All right. And so, and under certain pressures too. If the pressure is too low, like we have these ranges. And so that's the state of the system and their macroscopic properties. And we get more into that in Chem 2. All right. What I really want you to know is that the change in internal energy right here is equal to the heat and the work. And we're going to focus on the heat most. All right. First law of thermodynamics. Energy can be reverted from one form to another, but cannot be created nor destroyed. Now, that is a little bit different than what really we accept now, right? We accept now that there's a law of conservation of mass and energy, right? So we obviously like E equals mc squared, right? Nuclear takes mass and makes energy. And so what has happened is the law of conservation of mass and the law of conservation of energy are basically combined to the law of conservation of mass and energy. All right? Okay? So that's kind of what that is. But we're going to just roll with the first law of thermodynamics, which means the energy of the universe is constant. Which is kind of weird, but that's the way it works. All right. Work and heat. All right. So now look at this. The universe has so much energy, and we are always going to transform it. Now, a system, whether it's you're drinking a beverage, whether it's a hot beverage or a cold beverage, right? Let's say you're drinking a hot beverage. It has heat. And if we just leave that beverage there for a while and come back to it, it'll cool down, won't it? If you have a cold beverage and you just leave it there for a while, it'll warm up, right? But both of them have what we call internal energy, right? The hot beverage has more internal energy than the cold beverage, but they both have internal energy. And that's because the particles of the beverage are moving, right? Now, the energy is random, right? So there's no direction. It's like chickens with their head cut off expression, right? The particles just moving everywhere. They're not organized at all right? And we call that thermal energy. So your hot beverage has more thermal energy than a cold beverage. If we heat the cold beverage, we will give it more thermal energy. All right? So thermal energy is the particles are moving in a system, and work is organizing that motion. Right? We organize that motion. So the car is a very easy visualization of this. You have however many cylinders in your car, usually 4 up to 16. Now, most people don't have 16 cylinders. They're not driving Bugattis, but maybe you are. Good for you. Great machine. But most of us have 4, 5, 6, 8, that type of thing, right? And if you have, no matter what you have in your cylinders, gasoline is usually injected now. It's fuel injected. We still have a carbureted car, but most of the time they're fuel injected. And if they're injected with fuel and air for oxygen, right? And so then all of a sudden the piston is making the chamber where that gas and air is as small as possible. And then the spark plug ignites and boom, sends that piston down towards the ground or towards an angle, right? Usually. Depends how it is. There's some weird cars that are not, but usually the piston goes down towards the earth in some way or form. And you just create more volume. Well, when that gas burns and expands, right, because it's in a cylinder that expands, that's organized motion. So the burning of the gasoline, those particles are, that's random, incoherent motion, right? Just fire. Fire is just random, right? It doesn't have a direction to it. You sit around a campfire, it gets warm on 360, right? Below it, I guess the ground gets hot, right? Above it is hot, and then all around it's hot, right? And usually your feet are hot and your face is cold, one of those campfires, right? So in your car, that explosion of gasoline and air and oxygen is random motion. But the cylinder goes in a very organized motion as it expands. And that's work. All right? And so work is what we want. So we take that heat from the gasoline and air and make it into work with the machine of the engine. Kind of neat. All right? Okay. And so let's just recap the units. All right? So force is mass times acceleration. All right, Newton's second law, F equals ma. So kilograms times meter per second squared is capital N for Newton. Then energy, right, is defined as force times distance, but that's not necessarily true. Work is force, spelling, times distance. All right? So W equals F times D. All right? And that's a kilogram meter second squared times a meter. Kilogram meter squared second squared, which is a Newton meter, which is a joule, right? Now, work is also negative P dV, negative pressure change in volume. Okay? And that's the car example we just talked about, right, where that cylinder expands because an expansion, right, of the cylinder, right, it got bigger, but right, we're actually doing work on the system, and so, we're not going to do a lot of that in here. I'm just showing you that it works that way. And so 101.3 joules is 1 liter times an atmosphere. And then energy has the same unit. Energy has same unit as work. And then finally, power. Power is the rate of work or energy usage. Right? And so power is work or energy divided by time. So that's a kilogram meters squared per second cubed, which is a joule per second, which is a capital W for a watt. All right? And so work has the same unit as energy. Oh, I wrote that twice. Sorry about that. All right? Now, an older unit is the calorie. And so by definition, a calorie was you took 1 gram of water, weighs 1 degree Celsius. What's the energy required to do that? Well, it's a calorie. Now, note, food calories equal 1,000 calories. Right? So our food calories are a kilocalorie. We need a lot of energy. All right? We need a lot of energy to do this, okay? To operate, which is good because it's the way we work, all right? So we'll do some examples. What is heat? So what is heat? Heat, before I dive into this, pause and try to do these 3 examples, and then we'll do them. All right. So heat. Hopefully you pause. All right. Heat is thermal energy. Right. Total amount. And just so you know, temperature measures thermal energy. And we're going to, here's some foreshadowing for you, right? You can have aluminum foil in the oven at 350 degrees Fahrenheit, and you can touch it and you do not get burnt. All right? If you touch the inside of the oven at 350 degrees Fahrenheit, your knuckles get burnt. What's the difference? They're both at the same temperature. Well, the aluminum foil has a lot less thermal energy than the oven does, right? And we're going to show you how that works later on, but that's an example. So 2 things can be at the same temperature, but they can have different amounts of heat, all right? Just like, again, you go to a sauna. If you guys like a sauna, maybe you like a sauna, maybe you've never been to a sauna. You sit in there and it gets really, really hot, all right? It's usually that like wood-looking box with something in there, and it's hot and dry. Well, you can touch the air in there that's pretty warm, and you don't get burnt. But if you were to touch, if it was water in there that was that hot, it would not be good, right? And so that's where things that can have the same temperature but different amounts of heat. All right. So that's how heat is the amount of thermal energy, right? Okay. All right. The total amount. And so under what condition is heat transferred from one system to another? It's always hot, right, which is more thermal energy, to cold, less thermal energy. All right? So it's always hot to cold. All right? All right. So hopefully that kind of makes sense. Heat's transferred hot to cold, and I think we already knew that, right? That's how we get burnt. All right. And then heat is the total amount of thermal energy. Temperature measures thermal energy, but heat is the total amount of it. Okay. So in a gas expansion, 36 joules of heat is absorbed from the surroundings. All right. So delta U equals Q plus W. This is Q, 36 joules. All right. Energy of the system decreases by 182 joules. So delta U, right here, is negative 182 joules. So what is W? All right. So if I subtract negative 36 joules, negative 36 joules, all right, looks like W is 218, negative 218. All right, so that would be the work done. All right, we got to calculate Q. So we're going to calculate Q here and determine whether heat is absorbed or released when a system does work on the surroundings of 64 joules and the change in internal energy is negative 23. All right, so let's dive in. Delta U equals Q plus W. Okay, we know what delta U is, and that's negative 23 joules. We're calculating Q. It tells us that, Q. Now, work. Work does, the system here does work on the surroundings. So what does that mean? If I have a system, I have surroundings. If the system does work on the surroundings, that means that the system is doing work, so W would be 64 joules, but is it going out or is it coming in? That's the question. All right. Now, it looks like since we're doing work on the surroundings, if you're doing work on something, the work is going out, right? So we're going to be going out. So energy is coming out of the system into the surroundings. Sorry, work is coming out of the system into the surroundings. So W is going to be negative 64 joules. So if we do that, Q would equal, looks like 41 joules of energy. So that means that heat is absorbed by the system. All right. Well, that's it for today. Let me know if you have any questions. Feel free to reach out. Until next time, guys, take care. Bye.